So by Sérgio Fenley, Foliations with Good Geometry.
Is this on? Okay, so I'm going to talk about foliations with good geometry. Okay. So I want to thank the organizers for inviting me to give a talk here. It's not on? So I'm going to, there's quite a few aspects of geometry of foliations, and I'm going to mention three of them here. Okay, so the first aspect is this seems to be on and off. Talk now. Hello? It's not on.
Let's change the frequency here.
Very sick patient.
Okay.
You talk now? Stay clear.
Okay. I think it's fine.
Is it on now?
No, actually now it's not connected to this system. You'll have to speak loudly. Otherwise,
So why do I need this?
oh, that's for that. We're videotaping you.
All right.
Maybe just let me take this one. Maybe the battery is dead. Or maybe it's not. Is it like that?
Can you hear me? Yes. Looks like it. All right. Where was I? Okay, so first the intrinsic geometry of leaves. I think most of the time I'm going to talk about, going to mention one foliations in three men. Okay, so this will be two-dimensional leaves. Okay, so it turns out that in a lot of situations, the geometry, the intrinsic geometry of the leaves is as you can sort of the form, the metric, and the manifold, so that the geometry is one of the standard types, so elliptic, Euclidean, or hyperbolic. Okay. And this is the most common case. So I think Etienne-Gilles is going to talk about this and other things, but he's going to certainly mention this is related to the uniformization foliation. So this is the intrinsic structure of the leaves. Okay. Another aspect of this geometry of foliations is the transverse geometry. Okay, so we look at, so locally here's my leaves, and I want to know what happens as I move. So as I move along these leaves, what happens to nearby leaves? Do they diverge? Do they converge? So what's going on? So, so convergence of leaves or divergence. So this is now in the sort of transverse direction, not the tangential direction to the leaves. Okay. So one of the things that there's here's this holonomy invariant transverse measures. In some cases, the use of holonomy invariant transverse measure can actually understand everything that you want to know about the foliation. And where do they converge, where they diverge, that turns out to be important in a lot of situations. Another thing that is a topic here is, so how does geometry change in the transversal direction? So foliation, if it's transversely orientable, we can choose a transversal vector field, and just for simplicity, let's think in the case when the transversal vector field, you can define a homeomorphism from one leaf to the other. I guess it's easiest to think of this in the universal cover. So we're going to have two leaves in the universal cover, and by integrating this transversal vector field, suppose that you can get a homeomorphism from one leaf to the other. Okay? How does that change the geometry? How does this compare with the geometry? The sort of the simplest case I'm thinking about is the case of vibration, where you do have this, and you're going to glue it back. So when you have a monodromy, and the monodromy, by understanding the monodromy, you can understand a lot about the structure of the manifold, in fact. Whether it's pseudo-anosal monodromy, irreducible monodromy, or periodic monodromy. Okay? And this also has, it's important you can say stuff even if you don't have a homeomorphism between everything, but sort of partial sets, So we suppose that a part of this leaf goes here, but there's more that goes to other leaves and so on. So even in those situations, you can say some things. And actually, I'm going to mention something about this later on. Okay? All right. So in the third topic, which is the embedding of leaves in manifold in relation with the geometry of the manifold. Okay, so in a way, these first two things are more sort of the structure of the foliation, and here I'm going to be looking, well, how do the leaves relate to the manifold that it's sitting on? Okay, and so I want to know if the leaves reflect the geometry of your manifold. So I guess I should thank Dave Gabay, because he talked a lot about the topology of foliations and how the leaves, or how the foliations, the Rabelais foliations, reflect the topology of your manifold. In the same way, I want to ask, well, how do the foliation or the leaves reflect the geometry of the manifold? So I'm going to be thinking in terms of geometry here. I'm going to be thinking in terms of distance. Okay. So I want to compare the path distance along leaves with the path distance in the manifold. So I want to know if I'm at distance 100 in a leaf, do I know anything about what is the distance in the manifold? Now, to start, I should put it in the right setting, because most foliations have non-compact leaves. And I'm going to be thinking about, actually, closed manifolds. So compact manifold, which has bounded distance between all points. So, of course, after a while, if you're far away in the leaf, you're not going to be reflecting geometry in the manifold at all. There's no way you could do that. But you can if you lift to the universal cover, or in the same way you could think in terms of homotopy classes. Okay? So not distance in M, so it's better in the universal cover. Okay? So here, so let's just get some examples here to see. So for instance, there are linear foliations of the three-dimensional torus, which when you lift to the universal cover, they're just going to be a foliation by parallel planes. In the universal cover here is R3. Okay? So these are totally geodesic. Okay? The distance that I see here in the leaf is exactly the distance in the manifold. Okay? So this is the best possible. So where the foliation is exactly reflecting the geometry of the manifold. Okay? So there's examples in the three-dimensional torus, in S2 cross S1, and in T2 bundles over S1. There's lots of examples. but it turns out that they are not that common. So one big problem with this totally geodesic is that it really is a big requirement. First, you have to choose the metric right. So if I change my metric in the torus, then these leaves are not going to be exactly totally geodesic. Second, if I isotope my foliation in the torus, then they again are not going to be exactly totally geodesic. Okay? So I want to relax that thing. So, well, there's lots of ways that you could. Do I want this down or not? Well, so one way to relax is to talk about quasi, not totally geodesic, but quasi geodesic or quasi properties. Okay. So let me give sort of one of the main definitions here. So a map F between metric spaces is a quasi-isometric embedding so I want to relate the distance here with the distance here, that they're not too far apart, but I'm going to relax a little bit in the following ways. So if there is a constant greater than 1, so that for any points here in N, and I look at the distance between their images, and I want them to be not too far from the distance of the respective points in N. So this is what I want. The additive part here is just to say that I don't care about relatively small distances, okay? But except for that, if you think big distance, really what we're seeing is that this, the distance doesn't grow too much and doesn't increase too much, okay? So that's multiplicatively boundedly related, okay? So in particular, if you have something which is totally geodesic, it's actually going to be satisfy this property. So let me define what I mean here by quasi-isometric foliation. So a leaf of a foliation is quasi-isometric if any lift, when we have the embedding in the universal cover of M, is a quasi-isometry. So I'm thinking about the path metric here, not induced metric. Okay? And the foliation is quasi-isometric if there is, so if all leaves are quasi-isometric. Okay? So I'm going to look for quasi-isometric foliations. And now let me talk about a little bit about which one class of manifolds that I'm particularly interested in. Rabless foliations in cipher fiber spaces have been understood for quite a long time by work of Thurston and others. Also in manifolds which have solvable fundamental group, they have been fairly well understood, or relatively well understood. So the remaining case is what happens when the manifold M is hyperbolic. So I want to sort of understand foliations of hyperbolic manifolds, and in particular in that case, for hyperbolic manifolds, what's the metric is important, in particular the metric universal cover and the asymptotic metric, or the asymptotic geometry there, okay? All right, so first there's a result by Zagib that there's no totally geodesic foliations in closed hyperbolic three manifolds. And his result is actually much more general. Even for totally geodesic laminations, they can only be a finite union of closed leaves, totally geodesic leaves. Okay, so this is a very general result. Okay, so the question is whether there's quasi-isometric foliations, and later on I'm going to mention a little bit more. Turns out that the quasi-objects in hyperbolic manifolds are extremely good. You know, they're very useful, and they give you a lot of information. Okay, so let me mention here the first result. So which is so there are no quasi-isometric foliations in hyperbolic closed free manifolds. So even if you relax to that condition, just bounded distortion in the metric, you still can make it work in the case of hyperbolic closed free manifolds. Okay? So I'm going to talk a little bit about how this goes, because it's interesting. It's actually sort of the easy part here. And then actually this introduces one concept which is very important for us later on. Okay? So we're looking at the universal cover. Okay? So here there's my foliation, the lifted foliation universal cover, and it has a leaf space. Which is, let's denote this by H, okay? So I'm thinking a condition for quasi-isometric to work is that the foliation be rabless, okay? So this, when you have a rabless foliation, when you lift the universal curve and take the leaf space, this is a one-dimensional manifold with countable bays, but maybe not Hausdorff, as Dave Gabay was explaining to us yesterday. Okay, and turns out that whether it's Hausdorff or not, it's sort of the key distinction here to understand this theorem. Okay, so let's see. One case is actually very easy. So suppose that H is not Hausdorff. And I'm going to show then the foliation cannot be quasi-isometric. Okay? So if it's not Hausdorff, so we see you have 2 points here which are non-separated. Okay? So they're limited of different leaves. And we can get sort of a picture which is there's these two distinct leaves, F and L, and leaves which are converging to F and L and maybe other leaves. Okay? So let's get points here, X point here and Y point here, and then, well, let's see this leaves, say, Fi, which are converging to F and L. Okay? Now let's get points here, Xi, and similarly Yi, so that the Xi is in Fi converges to X as I converges to infinity, and the same thing for Yi converges to Y as I converges to infinity. Okay? So the distance between, in the manifold, or the ambient manifold between Xi and Yi, this is bounded. Because the Xi is converged to Y, the Xi converges to X, Yi is converged to Y, so distance between X and Y is finite, therefore this is bounded. Okay? Now the distance between them along their respective leaves is converging to infinity. Because if not, if there's a subsequence where when it's bounded, then the disks of that radius around the Xi's are going to converge to a disk here on this limit leaf, and we're going to get that the Y is going to be in this limit leaf, so they would be in the same leaf. Okay? So we have this property here. And therefore, there's no way that this is going to be less than a multiple or constant multiple of this distance here. Okay? So this is not quasi-isometric. Okay? Well, that's sort of relatively the easy case. The other case, yes?
You mean for the leaves to be uniformly quasi-isometric when you say that the foliation is quasi-isometric?
Yeah, that's the good question. I was trying to hide. See, yeah, there's the question there that I kind of fussed around a little bit. I didn't put the same K here for all the leaves, okay? But, you know, I mean that actually here you can actually prove that there's one leaf, at least one leaf, which is not quasi-isometrically embedded for any K. Okay? So you look at this leaf here, okay? When you look at the manifold, project to the manifold, and look at this sort of this side here where the FIs are limiting, okay? So, oops, my L here. So if the L is sort of limiting, the pi of L is limiting on itself on this side, then you see that these are getting worse and worse quasi-isometric constants here. So if you get it sort of limiting on itself on this side, you get that the L is not quasi-isometrically embedded. If you have some element of the fundamental group of pi of L which has contracting holonomy, you get the same thing here. For the leaves here are contracting by some group of elements of the fundamental group, and then you're going to get the worse and worse, you know, quasi-isometric constant. And again, one leaf here is not going to be quasi-isometrically embedded. And if that doesn't happen, then there's a theorem by Topology that says that in the manifold pi of L is sort of the boundary of a product region. So you wouldn't see this picture here in the universal cover. Okay? So that's more of a technical point, but in fact you do get there's some leaves, at least some leaves, which are not quasi-isometrically embedded for any K. Okay? This proof doesn't say that there's no quasi-isometric leaves. For instance, if you have one of those foliations that Dave mentioned this morning, finite defoliations, there are lots of examples of those in hyperbolic treatment where the compact leaves are quasi-isometrically embedded. Okay? So you can have lots of quasi-isometrically embedded leaves. Okay? But not all leaves are going to be quasi-isometrically embedded. That's, I guess, what this proof is saying. Okay? So the other case, so the other case, I'm actually not going to do so many of the details in this case just because of time. So the second case is when the leaf space is Hausdorff and therefore is homomorphic to the real numbers. So that there are, I think, 2 or 3 steps here. So step 1, let's see, first, before I set that, let's see, the universal cover the manifold is hyperbolic 3 space, which is compactified with the sphere at infinity. We're going to use this a lot during the talk. And if you have any set here in H3, the limit set, which I'll denote by this, is the set of accumulation points in the sphere at infinity. Okay? So you're going to have those leaves, actually follows, actually I guess Dave is going to mention this tomorrow, but the leaves are going to be properly embedded in the universal cover. Okay, so they cannot limit in the universal cover. They can only limit here in the sphere at infinity. Okay, in this compactification. Okay, and the places where they limit is the limit set. Okay. Now it turns out that if you have a fibration, the limit set of any leaf when you leaf to the universal cover is going to be the whole sphere. So this picture is very misleading. You know, as you go out towards infinity, you know, the leaf becomes more and more dense in the sphere at infinity. Okay, and it's kind of hard to understand what's going on there. So step 1 is to show that in fact, whenever you have this property, the limit set of every leaf in the universal cover is the sphere at infinity. So step 2 is to understand the intrinsic geometry of the leaves in this case. So I'm in a hyperbolic 3 manifold and they have a rabless foliation. So there's a classification of foliations. So either you're going to have a sphere leaf, which we cannot have because this manifold is irreducible, or we're going to have a transversely invariant holonomy measure of Euler characteristic 0. I'm not going to define this, but the important fact for us is that that can be approximated by an incompressible torus, which we don't have because the manifold is hyperbolic, Or the third option is that every leaf of the leaf defoliation is uniformly Gromov hyperbolic. And in fact, we know much more now by results of Kandel. We can put a metric in the manifold so that every leaf is actually hyperbolic with curvature equal to -1, okay, everywhere. But all I need is this. If the leaf is Gromov hyperbolic, that means that the leaf is quasi-symmetric to the hyperbolic plane, and there's a compactification with an ideal boundary, and this is a circle, and this compactification is homeomorphic to a closed disk. Okay, so it's sort of like this situation here. I have an ideal boundary here. Okay. All right. So this is step 1, step 2, and step 3 is. In this case, actually, the conclusion is going to be a little stronger, in the sense that there's not going to be any leaf which is quasi-asymetrically embedded. So let me assume that there's some leaf. So if there is L, which is quasi-asymetrically embedded, okay, so we have an embedding here, which is a quasi-isometry. Now this is a Gromov negatively curved. Oops, this is universal cover. This is H3. Okay? So one of the first and basic results of Gromov says that when we have a quasi-isometry between negatively curved or Gromov negatively curved manifolds, then this extends to an embedding between the ideal compactifications. Well, it should be L here, I guess. Okay, and the image of the ideal boundary here is exactly the limit set of L. Okay. So what this is saying is that if this holds, this is a circle, so this should be homeomorphic to circle, or it's a Jordan curve. Okay? In particular, this contradicts step 1 that says the limit set of every leaf is the whole sphere. Okay? So we cannot have this. So in this situation, no leaf is quasi-asymetrically embedded. Okay? All right. So what can we say? Well, we cannot have quasi-asymmetric foliations in hyperbolic free manifolds. But so what can we say? So we're going to focus in this property here, which is called the continuous extension property. Okay, so we're going to look. The foliation we're going to be interested in, they're still going to have leaves which are Gromov hyperbolic, and we can still ask whether this can hold. So can this hold? Okay. Obviously, we're not going to require that this is an embedding when we're restricted to the ideal boundary. Okay, so we're going to only ask whether we can extend continuously, and that's exactly what Cannon and Thurston did in their paper, their work in the 80s, 85 or something, and they proved that that happens for vibrations. Okay, so let's talk a little bit about that. So there was the first question, whether there was quasi-asymmetric foliations. Then there's this question 2, which is can leaves the leaf defoliation extend continuously to ideal boundary? And there's a yes answer for vibrations, over the circle by Cannon and Thurston. Around 85. And so where they show that when you lift to the universal cover, the leaves extend continuously. Now, that in that case, the vibration case, we have that the leaf space is Hausdorff. So that the limit set of any leaf is the whole sphere. So, but still, the leaves extend continuously. So this produces what they call the grouping via piano curves, the sphere filling curves. Okay. Now, how did they do such a thing? Okay. So the way they did this is by looking at essentially the transverse geometry, okay? And in the following way. So a manifold of fibers over the circle. We can think of this as a manifold which is a surface cross I with a gluing map. Let's call this age between S. So this will be S cross 0, S cross 1. And they looked at when you glue, which type of map is this? For an hyperbolic manifold, it turns out that this map has to be what's called a pseudo-Anosov. And the underlying idea here is that as you move, you know, what's going on with the geometry of the leaves? Is it being preserved? If it's sort of preserved everywhere, you essentially have the case where you are in a, this monodromy here is periodic. So you get essentially the structure of a cipher vibration. Okay? If it's not periodic, but there's some regions where it doesn't stretch or doesn't contract, you're going to produce eventually a closed curve which sort of returns to itself. So you're going to produce immersed torus, which is incompressible. Okay? It's like a reducing case. And the last case is where, you know, no matter where you look, every closed curve eventually either contracts or expands. Okay? And so there's this contracting direction and there's expanding directions. And in fact, produce a lamination you can blow down to a singular foliation. Okay? Actually, you have two of them, stable and unstable. So the stable foliation, so that this is stable, they're going to be invariant by this map. Okay? So you produce actually a singular two-dimensional foliation here, so that when you go, say, forwards, the distances are contracted exponentially along this stable foliation, and when you go backwards, they are contracted exponentially in the unstable foliation. Okay? So this is what a pseudo-Anosov flow is. So they produce a pseudo-Anosov flow transverse to F. This is a suspension flow, which captures what's happening to the change in the geometry here of the leaves as you move along. Okay? And it turns out, let's see, this has two foliations. So they are singular. But the singularities are not bad. They're pretty well understood. They are, you know, like p-prong singularities in the plane, and locally do the product of that with an interval. Okay? So this is the singular local actually are orbits of the flow, closed orbits of the flow, and say this is the stable foliation, the other orbits are convergent here. Okay? So this is a three-pronged singularity. Okay? And there's finally many of those that are isolated and so on. So these are a singular stable and unstable foliation associated to this pseudo-Anosov flow. And I guess I should, for future use, that I'm going to refer to this again. So a pseudo-Anosov flow is one which has, away from the singularities, has, you know, there's the flow direction, there's one direction which is, say, the stable, which is contracted exponentially, and one direction which is unstable, which is contracted exponentially in the backwards direction. And the local picture along the singularities is more or less like this. Okay? Suspension pseudo-Anosov flow is one example. Okay? So the key property here was that they used was look at these foliations and ask the same question, whether they are quasi-isometric. And in fact, they could it was not too hard to show that these are quasi-isometric. So they weren't looking at the quasi-isometric regression for non-singular foliation, but actually they proved that there are some singular foliations which are quasi-isometric. And using this, so the key thing here is that, let's think regular leaves here. The regular leaf of this is just, when you leave to the universal cover, it's just a plane. And because it's quasi-isometrically embedded, then by the Gromov result, that means that the limit set is a Jordan curve, so it's a nice situation. And also because it's quasi-isometric, it's contained in a bounded distance from the convex hull of its limit set. So, for instance, you cannot have things which are like, this. They're far away from a fixed point, but they're still sort of big in the sphere of infinity. Okay? Because this would mean that they are not, see, this path goes a distance much smaller than having to go along the leaf. Okay? And using this, they can actually trap where the leaf of the foliation, the original foliation, the fibration here, is, and prove the continuous extension property. Okay? So, what I'm going to do now for the rest of the talk is going to try to do a similar scheme here, but not for fibrations, but for the finite defoliations that Dave was mentioning earlier today. Okay?
Before you erase, would you comment on step 1?
What?
Would you comment on step 1? So what is the whole sphere as a
Right. Well, quickly here. Let's see. So suppose it's not everything. Okay? So suppose you have some leaf, which is, the limit set is not everything, okay? And let's assume this transversally orientable just to simplify. And then there's a notion of, if there's a point which is not in the limit set, you can define whether it's above or below the leaf, okay? So look at, parameterize the leaves as LT where T is in R, okay? And look at UT, the set of points in the sphere of infinity above this L of T, okay? And then there's a simple relation. I think that UT is contained in UT prime if T is less than T prime, or the opposite thing, okay? And take the union of this UT where T is in R. This turns out to be pi1 invariant and not the whole sphere. And that's a contradiction because the manifold was closed, okay? All right, so let's see. Oh yeah, finite defoliations. So finite defoliations are foliations which reflect directly the topology of your manifold. Okay, so suppose that M is irreducible, orientable, and the second homology of M is not 0. So for any non-zero class in the second homology, there is a finite defoliation, which I'm going to say a little bit more about what it is in a moment. Labeless, so that the compact leaves represent A. Okay? So like Dave was pointing out, so finite def means that the leaves are properly embedded. Properly embedded means that they never limit on themselves. Okay? So there are some compact leaves, which are the depth zero leaves. They don't limit anywhere because they are compact. Okay? Okay. And then there's the leaves which limit on this compact leaves by the spiraling procedure that Dave was describing this morning. And if they only limit on compact leaves, they're going to be called the depth-one leaves. And then there's leaves which limit on the depth-one leaves, and then, of course, they're going to limit on the depth-zero leaves, and so on. And if after finally many steps you've taken up all of your leaves of your manifold, then this is going to be what's called a finite defoliation, and the depth is actually the biggest depth that you get. Okay? All right, so Dave showed that whenever the second homology is not 0, you get these foliations, and they are, like Dave was describing, they are associated to a hierarchy of the manifold. This is what you will get by cutting first the manifold along this leaf, and then looking at the depth on leaf, and since it spars along here, you can collapse, after a while you can collapse here and think of it as a leaf which ends here. That's a surface in sitting in the cut-up manifold. And that's how you obtain the second surface and so on. Okay? So they are directly associated to a hierarchy of the manifold, which is in the sutured manifold world, which I'm not going to get into. Okay? All right. So this is Gabai. And then after this, there's the result of Gabai and Mosher, which was very similar to that, even though much more complicated, to look at the transverse geometry of F, and looking at what happens as you move. You know, it's is everything staying the same, or are there regions which are being contracted and expanded? It turns out that if the manifold is hyperbolic, let me state it just for hyperbolic. Then they prove that there is a pseudo, a Nassau flow phi, which is almost transverse to F. So almost it's a technical condition that I don't want to get into in this talk. Let's just, for the purpose of this talk, let's just think transverse. Okay? And this has the stable and unstable foliations associated to it. It's a much more complicated situation than getting in the vibration case, which is a case where everything works beautifully. You don't get into trouble. So I was trying to follow the same scheme and see if these foliations could be quasi-isometric. And in my PhD, I actually did this for some depth-on foliations. But by not looking at the whole manifold, but just looking at the region where you have the depth on leaves, because you still have a sort of a vibration there in the subset of the manifold. But that turned out to be very complicated when you have higher depth, and I didn't know what to do. So I decided to go in a different direction. And in fact, in joint work with Limos, what we did was not look at this directly, but first look at the flow. Okay? So this is sort of an intermediate step, which actually talks about the geometry of flows. Okay? And this is joint work with Limosher. So those flows, such pseudons of flows, are what's called quasi-geodesic, which means that flow lines are quasi-isometrically embedded. Okay? So the flow lines are quasi-geodesics. So quasi-geodesics means, quasi-isometrically embedded, which is if you measure distance along the flow line and measure distance in the universal cover, they are boundedly related. Okay? In particular, they have well-defined ideal points in forwards and backwards direction, and they are a bounded distance from the geodesic which connects this ideal point. The ideal points are distinct, and the flow line is a bounded distance from this geodesic. I should say uniformly here. There's a K which makes all flow lines K quasi-geodesic. Okay, So the bounds here from the flow lines to the geodesic are all, the distance are all uniform the same. Okay? So that shows that at least you can produce flows for which the geometry is good. Okay? Now, what about the defoliations? Okay? I'm not going to talk about this. It takes a while. This result uses a lot of the topology of the foliation. Particularly uses a hierarchy, the hierarchy associated to the foliation, in order to start with the top depth leaves to prove that the flow lines which only intersect those leaves that are quasi-geodesic, and by induction you prove that more and more leaves, flow lines are quasi-isometrically embedded, and then you get, in the end, you get all of them quasi-geodesics. Okay? Now, what about this 2 here? It's not the same to say that the flow lines are quasi-geodesics. Doesn't imply that the defoliations are quasi-isometric. But implies something, okay? What is it that I should say? It implies one thing. The leaves of stable and unstable foliations are Gromov, hyperbolic. So for non-singular leaves, so for instance the stable foliation, what I see is that there's all these flow lines. They are asymptotically convergent, so they in their leaves they're going to limit on with a single ideal point. Their negative ideal points are going to define the other ideal points of this leaf here. This is very much like the picture of H2 with all geodesics which have this as one ideal point. Okay? That's the picture you should have in mind. If you have singularities, then you're going to have sort of half leaves like this. So you have, this is one half leaf. This is sort of like a half plane foliated by this geodesics, but then you're going to have a few more of these glued along this singular orbit here. Okay? So in this case, the ideal boundary is a circle. In this case, is this theta curve or more complicated graph. Okay. So one thing that is true, that the flow being quasi-geodesic implies that the continuous extension property for the singular foliations, okay? So this leaves the map of this into the universal cover, extends continuously to the ideal boundaries, okay? Now, let me just say a couple of words about this. The ideal points are ideal points of flow lines. So you know where to map them because the flow lines are quasi-geodesics and they have well-defined ideal points, okay? So you pretty much know how to define the map. And using the property that the flow lines are uniformly quasi-geodesic, you can show that this map is actually, the extension is actually continuous, okay? All right. All right, so I know this, but I want a stronger result. I don't want just that they have the continuous extension property. I want them to be quasi-isometric. So let me state that result. So let's see that. Oh yeah. So let's be a quasi-geodesic pseudo-nozzle flow So for this result, I do not need that this quasi-geodesic pseudo-nozzle flow comes from a finite defoliation. Okay? It's just a result about pseudo-nozzle flows which are quasi-geodesic. Okay? Then the stable foliation is quasi-isometric if and only if the leaf space of the lifted foliation is Hausdorff. Okay? So, given that the flow is quasi-geodesic, okay, which is already a very strong property, the foliation now, the stable foliation is going to be quasi-isometric if and only if the leaf space in the universal curve is Hausdorff. And we know that this is a necessary condition by exactly the same proof that was given in the beginning of the talk. Okay? And the same result for the unstable foliation. Let me give a couple of ideas here. So let's see. Well, this, we know it's true, so we want to prove that if the leaf space is Hausdorff, then the foliation is quasi-isometric. So actually I'm going to do the opposite. I'm going to show that if this is not quasi-isometric, then this is not going to be Hausdorff. Okay? So first step is that this is quasi-isometric if and only if the extension map, so because the flow is quasi-geodesic, I know that the leaves extend continuously, okay? And I know that if this is quasi-isometric, by the Gromov result, I know that this has to be injective, okay? So this being injective is certainly a necessary condition for this foliation to be quasi-isometric, and it turns out that it's sufficient, okay? Let me not explain too much here, else I won't have time for anything else. And step 2, if there is an L in the stable foliation with this extension not injective, then we produce some branching in the leaf space of the stable foliation. Okay? All right. Now, what good does it do for us to replace this condition by this condition? Okay? So at first you might think, well, this doesn't seem to be any better than that condition, since I really don't know anything about this condition or this condition really. Okay? So let me say one thing first before I go on to say the result. This is a condition about the geometry of the foliation, which turns out it's very, very, very hard to check. This is a condition about the topology of the foliation, which in general it's easier to check. And in this particular case, you can actually have an answer. Okay, so let me give you the answer here. So the answer I'm looking for is, if this is not Hausdorff, what can I say? Okay? So if it's not Hausdorff and F and L in the stable foliation not separated, then I have these two leaves, F and L, which are not separated, so they're limit of other leaves here. So it turns out that there's a chain of leaves. There's a way to define an ordering in the set of non-separated leaves from any given leaf. So there's a chain of leaves which are all non-separated from each other. And this, they have orbits, so that when you look in the manifold, this is a closed orbit of the flow. And more importantly for us, these are all freely homotopic. So the only fact that I want to get at this point is that if this is not Hausdorff, then I produce closed orbits of the flow which are freely homotopic. Okay? And then I should say that the additional work comes, well, now we're reduced to looking for freely homotopic closed orbits of the flow. And that's something that we can check in all our cases. So there are many examples. And I should say here the flow is transverse to a depth 1 foliation, where there are no freely homotopic orbits. And if there are no freely homotopic orbits, this is Hausdorff, and if this is Hausdorff, the stable and the stable singular foliations are going to be quasi-isometric. Okay? So using this, I produce examples of quasi-isometric singular foliation, which are not the singular foliations associated to suspension of pseudo-nozzle flows. Okay? So the quasi-isometric question, for non-singular foliations, you can never have them in hyperbolic manifolds. But if you allow singularities, then you can have them associated to suspensions and associated to more complicated foliations. Okay? And the last result that I want to mention is what happens to the original finite depth foliation. Okay? So we know that that one cannot be quasi-isometric, but can it, the least, can they extend continuously to the sphere infinity? And it turns out that there's an answer. And this theorem takes a while to state. I'll probably just have time to state it. So let F be a finite depth Rabless in M3 closed hyperbolic. So let E be pseudo Anosov flow almost transverse to F. There's going to be two hypotheses. So first, suppose that the singular foliations are quasi-isometric, and we have examples of that that I just mentioned. So in addition, I'm going to suppose that the flow is actually transverse to F. Probably this doesn't make any sense for anybody except for Lee Mosher here, because I didn't say what almost transverse was anyway. But there are situations where this is which is actually transverse to the foliation. Okay, and actually there are the same examples that I was constructing there. Okay, then the leaves of the lifted foliation. So these are sitting in the universal cover, which is H3, extend continuously to the sphere and infinity. Okay? So in this way, there's all this object that are playing around together. So we have the foliation, the non-singular foliation, which is finite depth. You look at the transverse geometry of this foliation, you produce this pseudo-Anosov foliations. Okay? Under various conditions, you can show that these have good geometric properties, and then you can use those to derive properties of the original foliation. Okay? I think that I'm going overboard, so I'm not gonna have time to explain this. If you want, I can explain it to you later. Thank you very much.
Are there any questions?
What is almost transverse after all?
Almost transverse, good question. The construction of the transverse flow is really done in sort of in the lamination world. And laminations work fine to get the stable and unstable laminations transverse to F. But when you want to get the pseudo-Anosov flow, you have to blow down some things. And when you blow down, sometimes you're forced not to be transverse to the foliation. But the only obstruction is that I'm only going to give you the simplest one of the simplest things that could happen. A little more complicated could happen. So you can have a pseudo-hyperbolic orbit like this, for instance, which there's no way, this is a closed orbit, there's no way you can make it the foliation transverse to the flow, but if you sort of blow up this into, I'm introducing an annulus here. So this was a closed orbit, I'm going to blow it up to an annulus. And now, oops, I don't know if I did it. Maybe the arrows are not quite right. So, but the thing is that I blow up this annulus here, and now this was where there was a trouble. And when I have this annulus, now it can be transverse defoliation. So up to this blow-up procedure is transverse. Okay? And for a lot of things, for the geometric properties, it really doesn't matter. The foliation associated to this are going to be quasi-geometrically embedded, if and only if this foliation is quasi-geometrically embedded. For the dynamics, this is better because you have the very well the stable foliations and so on. But for the geometry, this is as good as this. Okay?
So the pseudo-nozzle flow always has a transverse measure.
The pseudo-nozzle flow.
These foliations